Well, welcome to today's lecture. As I promised, I wanted just to quickly show you how you can make a gear, the 3D model of a gear. It's good to build a 3D model of a gear if you want to print it or if you want to check if it is part of a gearbox, how it works, and it can be easily done. The software that I'm showing here is Autodesk Fusion 360. As you can see on the top, it says Autodesk Fusion 360. It's free for students. If you just Google Autodesk Fusion 360, you can find the link to download and the rest. Super easy to learn. It's way easier than SolidWorks and way better. And if you are thinking of joining industry in future, of course, this one is more popular than SolidWorks. The software to install it is very light. And another good feature about it is that you can work from different computers. So on your browser, or you can share, let's say if a team are working on a project, you can share. I'm not going to teach you the software, of course, but there are tons of YouTube videos. And again, if you are familiar with a 3D modeling software, such as SolidWorks, it takes you probably half an hour to figure out everything and you can make things. Like you can make complex part, let's say this mechanism, which is a spherical parallel robot. And you can see the motion, how these things is working, the degree of freedom. And you can do tons of other stuff, such as stress analysis, heat analysis, and many other things. Anyway, so let's get to making one gear. In this software, there is a feature for gears. Like here, you can see it. And if I open it, then I have different options like a spare gear, helical gear, bevel, rack, worm gear, and so on, internal gears. Let's say if I want to make a helical gear, I click on helical gear. And then a window pops up, ask for some information. What is module here? I should add here, let me move back to my notes for a moment. When we define pitch, there is another terminology people use, show it by M, which is the opposite of pitch. It's D over N. And it's common more for metric units. So this is for SI unit, and this is for more for not US units. But people use them interchangeably, and something that you should know. So it's called module. So this is module. Okay. So if you saw somewhere module, it's just the opposite of pitch, and it's unit. Of course, this one, it's millimeter or meter or centimeter. And let me write it by red. So the unit for this guy is millimeter, and the unit for this one is 1 over millimeter. But rarely people use unit and they just mention it. This is the pitch. Okay, let's go back there. I need to decide the module, and the software tells us what are the standard modules like available in the market, let's say, and then the number of teeth. So in other words, we don't specify the diameter, we just gives the number of teeth and the module. If you know the pitch, so you just inverse of that numbers gives you the module. The pressure angle, so two common numbers is one is 14.5 and another one is 20 degrees. 20 degrees is more common, but let's keep it as it is. And then the helix angle. the angle that each, because we are modeling a helical gear, right? And that was the angle between each teeth and the main axis. So this is your gear. And let's say if you want to have a shaft there, or let's make a bigger one. So I'll do it one more time. Helical gear, let's say we'll go for a bigger one, maybe 3. So module 3, let's say number of teeth, make them 20. And let's say the helix angle, make it maybe 25. And then the high of the gear, which by high here, it means for us, the width of a gear. So this is our gear. So again, this is the helix angle, so 20 degree. If you look at it like in this angle with the horizontal, it is 20 degree. And what else? So if you count the number of teeth, it should be 18. And the module is 3. So it means the diameter, you can figure it out, the diameter, right? So you have the module, we picked 3. The number of teeth, we decided to be 18. So we can find the diameter. And again, when you go to market to buy gears, they give you either pitch or module and the number of teeth. Nobody talks about the diameter. That's, you can figure it out. Let's say the same things if I want to put it on a shaft. So easily I can create, let's say, the hole for the bearing inside, maybe 10 millimeter. And then, as you can see, very similar to SolidWorks or your other software that you have, extrude or cut, whatever you want to do. So here is your gear. And of course, if you want to make a gear like in a pair, you make another one like that. And like me, you install it there. And then the software shows you if they are mesh. In other words, if your design is good and they are working together. For example, if I make 2 gears, but their modules are not the same, remember the pitch or the module must be the same. But intentionally, you can try it later if you pick the number of teeth, some arbitrary numbers, so the modules are not the same, then you will see it's going to be crazy and these things are not going to mesh properly. So that's about the gear. And let's say now you want to print it. And so all you need to do, you go somewhere, I believe there, yes. And then you say 3D print. And then it asks you which part you want to print. You say this part. You decide how good you want it to be. Should I send it to a printer? Not now. And then hit OK. It saves the file for you. Let's save it on a desktop. Let's call it gear 265. So this is the STL file. So it gives us the file. Here is the file. And now depends on which 3D printer you use. You can open it in the software to create the G code. I strongly recommend as a mechanical or manufacturing engineering, if you have some saving, buy a 3D printer. You can buy a good one for $200. I guess on Amazon, there are very good ones. If you don't know which one to buy, send me an email. I'll send you a link. Like by 200, 250, you can buy a good 3D printer. So it can be a good practice for you this summer. So, and then you decide for a bunch of things here, and then like how fast you want to print it, the quality, and so on. And then your file should be ready for printing to be sent to printer. You can view it to see how it will be printed. So of course, the printing will be layer by layer, and you can In fact, why my, okay, that's because of the Zoom. Zoom is on my way. So for example, here it shows you how the things is going to be printed, like using the, if I go faster, like here you'll see it's going to be like, because the speed that I selected, like layer by layer, it built the first layer, right? And then go to like the next layers, next layers, next layers, and it's going to be built like that. And you can see it's a helical gear, right? And it's been printed like that. Nice and interesting. Anyway, so that's about the gears in this software. And yeah, if maybe for your summer, start getting this software, Fusion 360, and watch some YouTube videos and explore the software and see if you like it, and then work on 3D printing. But for now, let's go back to our regular stuff. Which we were, where we were, I forgot. Okay, gear trains. All right. So any question, guys, before I start the lecture? No question? Are we good? Okay. So in that case, let me close this software. Do not save. Thank you. And thank you. And close this software. All right. So question in the chat. So the one that is called, so yes, Aiden. So for Cura-Rapidia, that's for the metal 3D printing, but you can also use the Cura, which is just for the like a regular printing. And again, it's free. So how cheap you can get a good metal 3D printer? It depends. So there are 3 types that we have. One type which use powder, it's called SLS, selective laser centering. They are in a range of $1 million, but you can print large parts and it does not require any support. It has a lot of waste though, because you have to use a lot of powder. The second type, it's used filament. It's more like plastic, like Mark Forged. I believe that's the brand. And that one, I believe, is in a range of $500,000. And when I say $500,000 is for the whole setup, because for printing, metal printing, you need the printer and you need the washing center to remove the chemical, and then you need the sintering. Because remember, for metal, after being printed, you need to put them in an oven so the particle sinter get close to the melting point and sinter together. So you get that rigid metal part that you want. And then another type that I have here at UBC, next September, you're welcome to come and check and use it if you want to print something. That one, I believe it's a range of $400K. So pretty expensive for now. But we are getting that somewhere slowly, that metal 3D printing becomes available even in, let's say, cheap and not at home, maybe but you never know, right? Because I remember like 5 or 6 years ago, even like a small PLA printer that I bought was very expensive. It was over $2,000. But now the same things you can buy it for $200, and everybody has one, and people start having a printer in their kitchen. I'm not joking. Yeah, people start having one, and so whenever they want to print something, they do. Yeah, if you want to use, you know, if you want to use for metal, the one at UBC is your best choice. And you guys, I guess, either in mech or in Manu, most likely you will take a course with me in your 4th year. The one course is on AI, and which partly in that course, I teach you how to use a metal 3D printer, because you are going to learn how you can monitor parts being printed. It's fun stuff. So you will learn how to use it. You will do a project. You will build something out of metal for yourself. So yeah, like next September, the first group of Manu and some mech students are going to take that course. It's 4th year. So, and the requirement is this course, by the way, it's prerequisite. So it's good that you guys are taking this course. All right, so enough about fun stuff. Let's get to the gear trains. Yes, 400 level courses. It's an elective course, so everybody can take it. And yeah, anyway. So last day we said we have 3 types of gears working together. Gear trains. What is a gear trains? When bunch of gearbox, like in a gearbox, when bunch of gears working together. And the goal here is to get from an input shaft. Let's say if you have a motor attached here, maybe not that one. Let's say if you have a shaft attached here, and we want to get the output there. So the omega in is here, and then maybe it depends on what we have, we can get omega out. And it gives us a gearbox. For a car gearbox, of course, we have, for one input, we have maybe 4 or 6 output, depends on how we change the gears. And the way it works, the gearbox has been designed in a way that you can switch gears. In fact, in this quiz, I guess this week you will solve one problem, which is like it shows a gearbox when you can switch between one gear ratio to another one. And our goal here is to find the gear ratio. By gear ratio, we mean omega in to omega out. What is this gear ratio? We can combine them in a simple way, which I showed you, all the gears in one plane, compound in parallel plane, and planetary, which I'll show you again with the small things that I printed, a demo, which has the sun, the planet, the ring, and the carrier, which we will get to that. And that's going to be the main focus of our this lecture and the next lecture. And by the way, Friday is a holiday, so the next time we will meet is going to be on Monday. I extended your quiz, so if you guys want to have a nice long weekend, so you can submit it by next Wednesday. Right? And it's going to be on gears. So let's start with the simple gears. Again, as you can see in this gearbox, all the gears being in one plane. Probably here you have your input somewhere, depends. Let's say maybe this one. And then you have your output somewhere there, maybe here. or maybe here. So you can have several output. You don't have to have one output. So instead of just one shaft coming out, like in the previous setup, maybe also they have another shaft attached here, maybe or maybe not. They will get another output there. So output 1 and output 2. Depends on the application. Okay. So how do we calculate them? Super easy. You saw we use the simple concept of instant center, and we prove that the ratio of omega, let's say 2 and 3, is equal to the ratio of their radius, the opposite, the inverse of their radius. If we multiply by 2, it's going to be diameter, and because we have the definition for P, pitch, N divided by D, and pitch for 2 gears must be the same. It is equivalent to writing at N3 divided by N2. And this is the fundamental formula that we are going to use. So omega, I'm going to write it down here for these 2 gears. So here, omega 2 over omega 3 will be N3 divided by N2. And we will use a negative sign here to indicate that these 2 gears, they change direction. So if one of them is clockwise, the other one is going to be counterclockwise. And you can easily visualize it. So internal gear, the same concept, the same formula, omega 2 over omega 3 is N3 over N2, but this time this guy is positive because the direction is not going to change. Okay, as simple as that. So we will use then the sign. Whenever you see a negative sign, it means changing direction, and positive means same direction. So what if we have several gears? No problem. We will start from the beginning and we will find our way to the end. Let's do this one here for the one on the left. So I will write the omega 2, when it gets to omega 3, first of all, it becomes negative, and it is N3 over N2. And then omega 3 transfer to omega 4, change direction, and it will be N4 divided by N3, right? Let me move the, oops, no. Now, if I multiply these 2 together, what do I get? Let's multiply them. I will get omega 2 multiplied by that. Okay, omega 3, we can get rid of that. It will give me N4 divided by N2. Am I right? Yeah. So what you notice here is there is nothing here, no sign of, in this final formula that we got, like the input to output, the ratio, there is nothing related to N to 3. So, and if you recall, I said in simple gears, the one in the middle, they are redundant gears. But redundant, not in a sense that they are really redundant. We talk about it because if we go from omega 2 to omega 4, like if we remove the middle one, still you get the same result. However, going always from a small gear to a large gear is not advised, because then it creates a large pressure on the smaller gear. So let's say if I had same gears here. Okay, that's good enough. If this is my 2 and this is gear 4, except the direction changed, right? But let's say if you want to keep the direction, like the top one, if you want to change it, we need to add another one in the middle. But in terms of ratio, the ratio will get the same. So my point here is the middle one is redundant. Let's solve the same things for the one on the right, and let's see what we will get. So if I write the relation between omega-2 and omega-3, I get a negative sign, N3, N2. What about 3 to 4? Please pay attention which one is connected to which. So the direction is not going to change. N4 and 3. Multiply them. You will get, so here is the multiplication, right? So if you multiply them, what would you get? Omega-2, omega-4, minus N4, N2. Yeah. So we'll see this one again. The direction will be changed at the end, but the ratio depends only on N4 and N2. All right, very simple. If you guys have any question, please ask. Otherwise, I assume that this is super simple and I'm going to move on. So Monday is a holiday too? I have to check. Because when I check on the status on, yeah, you're right, Easter Monday. Oh, okay, so lots of then holidays. So, okay, I will check the calendar. And yeah, you're gonna, I guess, prepare for the final maybe. But that's good, that's a good break. Okay. So let's get to better gears, the compound gears. Why do we need compound gears? As we discussed, first of all, because they are compact. Rather than having all the gears in one plane, now you can use parallel planes. And besides, it's not recommended to go for ratio 1 to 5, more than 1 to 5. Even 1 to 5 is not recommended. Again, let's move back one step here. Let's say if I want to go from gear 2 to 4, always it's recommended that the diameter of the big one, the ratio of the diameter of big one to a small one should not exceed more than 5. The diameter or the number of teeth, because then the smaller gear is going to go under lots of stress. So that's why if we don't have any choice, maybe we'd better go with the compound gears. And compound gears, I hope you remember from last lectures, the similar to simple gears, but we have parallel planes. So transferring power from one shaft to another. And with the compound, the velocity ratio can go very high. Similar to that little gears that I showed you, little motors that I showed you, the one before last lecture, the ratio, I believe, is 1/100, like that large. So this is something that you need to pay careful attention. This is what people show the gears on drawings. They do not show the teeth usually. They show a schematic in busy drawings, unless the drawing is just for one specific gear. So for simple gears, you know, they are all in one plane. For compound gears, they are in parallel plane, and this is the way we show it. The picture on the top, you see gear 2 is in contact with gear 3, and then 3 and 4, they are on the same shaft, right? 3 and 4, they are on the same shaft. So it means they have the same speed. and then 4 transferring its power to 5, and then the rest. In your textbook and in many drawing, people sometimes they use symbolic way to show gears. And you need to also know how to show gears like symbolically. All right. And it's in fact very simple for each gear rather than showing the whole cross section, like as it's been shown here, like the whole cross section. Instead, what people do is, can I use it? They just draw a line like for each gear. And then perpendicular to that, 2 lines to show that it is a gear. All right, so, and then this is the shaft. So that's about it. But let's calculate the gear ratio for this guy. I'm gonna emphasize that. So later when you see something like that, because remember in your exam or in future in drawing, they don't show all of these 3. They show just one of these 3 methods, like only the circles, maybe only the cross sections, or just a symbolic representation. So how do we calculate that? Similar things that we learned before. We start from omega-2 and we will find our way to omega-5. Let's do it together. So what is the ratio of, let me write it down here, omega-2 to omega-3, right? 2 is connected to omega-3. So first of all, the direction change, and then the ratio is N3, N2, right? So as simple as that. Then what else we know? We know that omega-3, when it gets to omega-4, nothing will change. They have the same direction because they are on the same shaft and the same velocity. Then my omega-4 gets to omega-5, direction will change, and it is N5 divided by N4, right? So we will use all these 3 equations simply and to find the ratio of omega-2 to omega-5. This is what we are looking after. So what do I need to do if I multiply these 2 again? And if I replace omega-4 here by omega-3, then I can get rid of omega-3. So it will be then simply N3, N5, N2, N4. And then it's going to be positive. So the direction is the same. And also you can double check always your answer. You do not rely on formula. Just visualize like the same way that this picture on the top shows. Visualize, okay, if my omega-2 is rotating clockwise, then definitely the 3 is going to be counterclockwise, 2 gears, visualize 2 gears. And then 4 is going to be the same as 3. And when I get from 4 to 5, it's going to be counterclockwise. Yeah, we start from counterclockwise and we get to counterclockwise, right? And look at the formula. This time, no redundancy. We use all the gears, 2, 3, 4, and 5. Right? Unlike simple, all the numbers are here now. And another way that you can double check always, I do, but you'd better always start from the simple formula at the beginning. Otherwise, sometimes there are some tricky questions and you may get confused. We will solve some of them. If you look omega-2 over omega-5, right? the odd numbers and then the even numbers, like omega-2, the even numbers, and then at the bottom I have N2, N4. And then omega-5 is the odd numbers, and then on like here I have N3 and N5, odd numbers. Some way to check it. However, it's so simple that you're not going to make, hopefully, mistakes. Okay. If you guys have any question, please let me know. Otherwise, I assume that this is easy for you, and I'm going to just move on to the next. So I'll give you a minute to think about it, and then we'll solve it together. Okay. This 1 minute gives me a good chance to drink my coffee. So what we want to find, we want to find out the ratio of omega-1 to omega-6. This is our input, which sometimes is called driver. And then this is our output, which is called driven. This one, it shows both like the circle one and the cross section one. And by the way, the compound gears can be a spare gear like this one, or they can be helical gear like these teeth to have an angle. And even they can be beveled gears. So, I'll give you the time to solve it, and then I'll get to that one. So start from here and find your way down to here. And the next one, and then the next. I'm thinking of next year in this course to run a competition and give some random gears to students, like team, and then each student design a gearbox, like by this combination of gears. And the winner is going to be somebody whose gearbox can lift a higher weight. Like each student team has a bunch of gears, a motor, like a small electrical motor, and then other tools, like similar to those that I showed you on my dock camera last day. And then they design something so they can lift with their gearbox a weight, the one that its gearbox has a higher torque ratio, then it's going to be the winner. So probably for that, I need maybe one undergrad TAs. If you guys are interested, let me know. So if you are really into gears and gearbox. Okay, who got the answer? I will write here, and then you can compare, see how far you could get. Let me check the chat. Yeah, Cameron got it right. 246,135, exactly. And the sign is negative. That's correct. Well, good work, Cameron. I'm sure many of you, other of you guys also got the answer. But let's see if we can find it. So start from the beginning, 1 to 2, and 2 and 1. And then this guy gives me 3 to 4, and 4 and 3. And this guy gives me 5 to 6, again negative, and 6 and 5. And also I have some extra information here, and those are that 2 is equal to 3, and also 4 is equal to 5. Super simple, right? So multiply all of them, do the math, is gonna be 2, 4, 6, 1, 3, 5. Again, the same patterns. See the odd numbers, omega 1, and at the bottom we have odd numbers. Just a way to check. But always, please solve the problem, because sometimes you're going to end up with tricky problems. For example, you may have another gear somewhere there. Here. Oops, not that one. Why it got like that? Okay. See, if you have gear 7 here, then your formula is going to be a little different. First, you need to find omega 6, and then from omega 6, you get to omega 7. So then it's not going to be like the odd and even number layout like that. And another thing that you need to be careful. So I leave it to you to find out. Then extra. This is a practice. Find omega 1 to omega 7. One more step you need to do, right? And another things, the gear does not have to be always, as I said, spare or helical. They can be a spare gear. For example, let's say on this shaft, if I have a bevel gear, or conical gear, whatever you want to call it. And you remember the conical gear, this guy make a cone. So they should intersect. Should have done a better drawing. Let's do a better job. Okay, one about here, one there. And another one there. So the same way, let's say this is gear 6, and now this is, let's call it gear 8, because we have 7 there, maybe on the other side of D, and we have gear 9 here. So this is, we have their N as well. Okay, so, and they are on bearing. So this is on a bearing here, and the same, this guy is on a bearing. Let's say if this guy is rotating like that from the top picture, then this one is going to rotate like that. So what happened here, not only the direction changed from counterclockwise to clockwise, also 90-degree change in the direction of the power. How we solve it? The same way. You treat the bevel gear in a similar way as like simple gears. Like here, there is no difference. The way that omega 8 gets to omega 9 is minus n9 divided by n8. So another extra things that you need to do, find omega 1 to omega 9. One extra, two extra work. Okay. So let's solve these problems together, and then we're good to go. We have 3 more minutes, and that's enough to solve this problem. I give you 1 minute to think about it, and keeping in mind that we have one unknown as well. You need to figure it out as well. But first, assume that you have all the n. Yeah. First, just write the relation. You want to find out omega 5 to omega 2. And then we will do something about that n2. So write the first one for this guy and then the relation for this and see what you will get. So if I write omega 2 over omega 3, it is minus n3, n2. And if I write omega 4, transfer to omega 5, n5, n4, right? And I know that 3 and 4 are the same. So from this information, you will get omega 2 divided by omega 4. Sorry, 5. We're looking for 5. You're not interested in 4, omega 2 over 5. It's going to be positive, and it's going to be n3, n5, n2, n4. And again, please pay attention. When we say it is positive, it means no change in the direction, but depends on which view you are looking at these two, right? Visualize this gearbox and imagine that you're looking from this side. This is your eyes. You have beautiful eyes, and you are looking, looks like an eyes, right? Okay. So when you look at this, this gearbox from this view, it is counterclockwise, right? You are standing the same place, and let's say magically you can see through this gearbox. So you will see the shaft is also counterclockwise. But if you come here and stand here, this is your eyes again, then you will see it is clockwise. So remember, when we say the direction from input to output, always we are staying in the same place. We're not changing our direction. All right, so that's the first things to keep in mind. So the problem solved. We know omega 2, omega 5. The question is n2. Oh, be cognizant of time. It's 51. We just need 30 seconds to solve it. But anybody can guess how we can find out n2? You can type it in the chat. n2 is unknown. Can we guess what is n2? No? So I'll give you a hint. What is the distance here? It is either d2 plus d3 divided by 2, or it is d4 plus d5 divided by 2. Do you guys agree? And what's the definition of pitch? It is d over n. Replace d by n, then it means n2 plus n3 is equal to n4 plus n5. So voila, you got it. Came French for a second. So from here, you can find n2, 26. Replace it here. And you will get omega 2 over omega 5, I believe 176, but please check my calculation. All right, so here is the lecture for today. Please go through example 2, example 3, and example 4 before the next lecture. And your quiz this week is going to be on everything that we taught up to this point. So there is not going to be any question on planetary gear. Planetary gear is for the next lecture. But in order to be successful in the quiz, go through these 3 super simple examples. Okay? And again, one more time, carefully review these, because in question in exam, you're going to have some question that the number of teeth is missing, but you need to figure them out using this information like the one that we used here. Okay. That's it for today, but I can stay in the room to answer your question if you have any question. And I'm going to chat to make sure that there is no question. Thank you, guys. Okay, so I assume you're all good. No question. In that case, I'm gonna stop sharing and I'm gonna say goodbye. All right, have a good day.